Let's continue. The problem number 8 is related to sensitivity analysis. The computer output of a problem is given below. Use this to answer the following questions. How much could the profit on X increase or decrease without changing the values of X and Y in the optimal solution? Now we have two tables, and it's saying the first table is saying this is the sensitivity output from Excel, and we have to find out how much. It's asking how much the profit on X increase or decrease without changing the values of X and Y in the optimal solution. We can see from here it's asking the coefficient 1, which is this one, its range. Okay, so it's very easy. You can see that C1 we can say is 5 plus 7, allowable increase is 12, and allowable decrease is 5 minus 1 is equal to 4. That's it. So this is the answer for this part A. Then the question is, if the right hand side of constraint 1 were increased by 1 unit, how much would the profit increase? Now that is what we call it shadow price. It's asking about that how much, if the right hand side of the constraint 1, which is at the moment it's 120, if it is increased from 120 to 121, then how much the profit will increase, and the shadow price is 0.75. So we can say that it will increase by $0.75. This is part B done. Part C. If the right hand side of constraint 1 were increased by 10 units, how much would the profit increase? So just multiply with 10, we have $7.5. When the question may be asked, is the right hand side, can we increase it to 10 units and still this shadow price is valid? Yes, the answer is yes, because Q1 has a range from 120 plus 120 is 240, and 120 minus 40 is 80. So we can see that within this range the shadow price of 0.75 is valid. If someone asks what is the objective function, what is the value of the objective function, optimal value, we can easily find out from here. You can say Z is equal to 5 is the coefficient, objective function coefficient, and the final value x1 is 35 multiplied by 30 plus 6 multiplied by 60, and that will give us the objective function value. So let's continue. Let's look at problem 9. We have some special cases here. Consider the following 4 LP formulation using a graphical approach. Determine which formulation has more than one optimal solution, which formulation is unbounded, which formulation has no feasible solution, and which formulation is correct as is. Let's look at formulation 1. We have the formulation here: 2x1 less or equal to 10, 2x1 plus 4x2 less or equal to 16, 4x2 is less or equal to 8, and x1 is equal to 6. Now if we see that the first constraint here telling us that x1 is less or equal to 5, but the last constraint is telling us x1 is equal to 6. This means there is a conflict here, and that's why we can say that it has a no feasible solution. So this formulation 1 is part answer to the which formulation has no feasible solution. It is the formulation 1. It is answer to the part C is formulation 1. Let's look at formulation 2. We have x1 plus 2x2, x1 less or equal to 1, x2 is less or equal to 2, and x1 plus 2x2 is equal to less or equal to 2. By looking at this formulation, we can see that this objective function here is maximization, and it has a slope of with x1 plus 2x2 is here, and the constraint has the same slope here. So most probably, if we just draw it, the constraint is active, and if the constraint is active, then of course, and binding, then of course we will have multiple optimal solution, because the objective function and one of the constraint, which is binding constraint, both have the same slope. So we can say that this is multiple optimal solution. More than one optimal solution, those formulation 2. Formulation 2. Let's look at formulation 3. It says maximize 3x1 plus 2x2 subject to x1 plus 2x plus x2 greater or equal to 5, x1 greater or equal to 2, and 2x2 greater or equal to 8. Now if we draw this, we can see that the constraints are, it's a maximization problem, and we have this one is greater or equal to 2, 5, greater or equal to 2, greater or equal to 8. Most likely, if we draw this, we will find that this has an unbounded solution. Let's draw that. We have first constraint is x1 plus x2 less or equal to 5. It's like that. Greater or equal to 5, sorry. It's on this side, x1 greater or equal to 2, and this one is like that. Okay, and x2 greater or equal to 8, which is x2 greater or equal to 4, is like that. So basically all is on the feasible region is this side, and since this is a maximization problem, we will see that you can increase your profit up to infinity, which means it is unbounded. So formulation 3 is unbounded, we can see that. Unbounded. Which formulation is correct as is, and the last formulation is if we draw it, it doesn't have any special case, so we can say that it is correct. By the way, a formulation where we have multiple optimal solution, which is formulation number 2, is also correct. I think there is no problem with that. The problem is with formulation 1, because it has no feasible solution, and formulation 3 is also having a problem because some constraint is missing. It is unbounded. Formulation 2 is also correct, but it has a special case of multiple optimal. Assignment problem. Now assignment problems can be solved with linear programming, although there are specialized algorithms which can solve assignment problems much faster than linear programming. Let's see, 4 clients have reached a law firm seeking legal assistance. These clients seek assistance in one of the following cases of divorce, corporate merger, embezzlement, and homicide. The law firm has 4 lawyers who have handled similar cases previously. The lawyers' rating in effectiveness from handling different cases is shown below. The law firm seeks to maximize the effectiveness by assigning 1 lawyer each to 1 case. Formulate the assignment problem. So we have 4 lawyers here, and we have 4 different types of cases here: divorce, corporate merger, embezzlement, and homicide. And each one has its own rating. Efficiency, we can say that, or effectiveness. Now we can see that we have to find out to whom each has to be assigned. Now this is a specialized algorithm in which we can say that each person is assigned one case. He cannot be assigned to another case. All right. And for this type of assignment problem, we will see a general formulation in the next slide, how to formulate these assignment problems. This is a general formulation. We define a variable called let xij is equal to 1 if I assigned to job j. Otherwise, we can say xij is equal to 0 if it is not assigned. So if the job is assigned, then we say 1, otherwise 0. Let Cij is the cost of assigning I to job j. Now it could be a minimization problem or it could be maximization problem. The problem of lawyers we discussed earlier is of a maximization problem. So in that case, we can say Cij can be representing as the efficiency or effectiveness or profit of assigning I to job j. And n is the total number of jobs or people, etc. So the formulation is that we minimize sigma I is equal to 1 to n and j is equal to 1 to n, Cij, xij, if it is minimization problem, or could be maximization problem, maximize this, all right. And subject to, we have, these are the constraints here. Xij is equal to 1, j is equal to 1 to n, xij is equal to 1 for I is equal to 1 to up to n is the total number of jobs or people. And as you can see that number of jobs and number of people should be same. So n is same here for I and j up to, and I is up to n and j is also up to n. And as said earlier that the total should be 1 because one person will be assigned to one job. So xij is equal to 1 for I is equal to 1 to n, and also xij is equal to 1 for j is equal to 1 to n. For all i's and j's, xij should be greater or equal to 0. This is a specialized special formulation for this kind of problems. Let's look at this, the earlier problem of lawyers, how to formulate. This was the general formulation. The particular formulation can be like this. To solve using LP, double subscripted variables are used. Xij, if if attorney I, if assigned to case J, or 0 otherwise, where 1, 2, 3, 4 are the attorneys, Adams, Brooks, Carter, and Darwin, and J is equal to 1, 2, 3, 4 for divorce, merger, embezzlement, and exhibitionism, respectively. And this is the maximize the effectiveness. We have the coefficients here. These are the effective ratings, okay, for each case assigned and person assigned to each case. And that's it. I mean, for example, here 6x41 is telling us Darwin has a rating of 6 in divorce, and similarly others. And these are the constraints that one person will be assigned to one job, or these first of all can be like that, and this is telling us that one job is assigned to one person, etc. Okay, and that's it. And of course all the variables are greater or equal to 1. greater or equal to 0. Transportation problems. Transportation problems are also can be solved with linear programming, and also there are specialized algorithms which can solve much faster than linear programming. But we will see how to formulate this kind of problems into transportation problem into linear programming. A bicycle manufacturing company has plants in two cities, New Orleans and Omaha. The New Orleans can manufacture 20,000 bikes and Omaha plant can produce 15,000 bikes per year. The company 3 warehouses are located in New York, Chicago, and Los Angeles. The sales requirement for the next year at the New York warehouse are 10,000 bikes, the Chicago warehouse is 8,000 bikes, and the Los Angeles warehouse are 15,000 bikes. The cost of shipping one bike from each factory to each warehouse differs, and these shipping costs are as given below in the table. Formulate this problem to solve by LP. So we can say this is the total supply here. New Orleans has 20,000 bikes, and this one has Omaha has 15,000 bikes. On the other hand, the destination total demand we have is 10,000 for New York and 8,000 bikes, and then we have 15,000 bikes for Los Angeles. Now if you add this comes out to be 35,000, and this comes out to be 10,000 plus 8,000 plus 33,000. So the supply is more than the demand. First, we will see a general formulation, as we have seen for the assignment problem, how to formulate this kind of problems. So we will see a general formulation for in LP, and then we can see particularly for this case. So the transportation problem, a general formulation. We define the variables. We say, and again, double subscript variables are useful in this kind of formulations. We say that Xij is the total number of units shipped from source I to destination J, and that Cij is the cost of shipping 1 unit from source I to destination J, and that Ai is the total supply from source I, and Bj is the total demand at destination J, and N is the total number of sources, and M is the total number of destinations. So we can see that J is equal to 1 to M, and sigma J I is equal to 1 to N, Cij, Xij. It is a minimization problem. Minimize this and just vary this, of course, the J's and I's, and you can get all the different combinations of that. Subject to, we have that the number of units transported, J is equal to 1 to M. M is the total number of destination, and you vary for I is equal to 1 to N, and A is the, of course, is the total supply from source I. And again, Ij I is equal to 1 to N, summation is equal to Bj, for J is equal to 1 to M. When you vary J from 1 to etc., and the summation should be equal to that B, which is the total demand at destination J. And Xij is greater or equal to for all i's and j's. Please note one thing, that the number of sources and number of destinations may be different. This was not the case with earlier assignment problem where the number of people and number of jobs were equal. Here, the number of sources and number of destinations may vary. Another thing to note is that this is a balanced problem. Here we have supply is equal to demand, because this is an equality constraint coming. However, if we have the supply is more than the demand, then the equality here will be converted to less than or equal to if supply is more. Alright. If on the other hand demand is more, then we will have equality here, but for this one we will have, if demand is more than supply, then we will have less or equal to over here. Alright. Less or equal to Bj. So that's a general formulation here. We will see the particular formulation for the case we have discussed earlier. So to formulate the problem using LP, we again employ the concept of double subscripted variables. We let the first subscript represent the origin factory and the second subscript the destination warehouse. Thus, in general, Xij refers to the number of bicycles shipped from origin I to destination J. Therefore, we have 6 decision variables as follows. And these are the different from destinations. From sources to destination. X1, one is the number of bicycles shipped from New Orleans to New York. X12 is the number of bicycles shipped from New Orleans to Chicago, and so on and so forth. Okay. And this is our these are the cost of transporting one bike, and X11 will be the number of bikes transported from source 1 to destination 1, etc. Alright, and subject to these constraints, we have the constraints are here. We have X11 plus X21, this is the demand constraints here. And this, as I said earlier, the supply is more than the demand. This is that's why we are using over here less than or equal to. And this is the total supply coming from New Orleans and Omaha, 15,000. That's it. I mean, if you just, of course, you cannot solve this with graphical technique. You need some computer software to solve this problem. And if you do it with Excel or QM for Windows, you will get your answer. The answer is over here. You can try yourself and get the answer. Okay, let's see this problem number 12, blending problem. The low NOx oil company produces 2 grades of cut rate gasoline for industrial distribution. The grades regular and economy are produced by refining a blend of 2 types of crude oils, type X100 and type X220. Each crude oil differs not only in cost per barrel but in composition as well. The accompanying table indicates the percentage of crucial ingredients found in each of the crude oils and the cost per barrel for each. Weekly demand for regular grade of low NOx gasoline is at least 25,000 barrels, while demand for the economy is at least 32,000 barrels per week. At least 45% of each barrel of regular must be ingredient A, and at most 50% of each barrel of economy should contain ingredient B. The low NOx management must decide how many barrels of each type of crude oil to buy each week for blending to satisfy demand at minimum cost. So we have these crude oil types, and two types of crude oils are there, X100 and 220, and their two ingredients are there in percentages, and the cost per barrel is also given to us. Now these are the crude oils, and we have to blend them to get another types of blending to get the regular and economy. So in this type of problem, the defining the decision variable is very important. That if you define the variables properly, then solving or writing the formulation is not difficult. So let's say x1 is equal to number of barrels of X100 blend to produce regular, and X2 is equal to number of barrels of X100 blend to produce economy. Okay, and then we define X3 is number of barrels of X220 blended to produce regular, and X4 is equal to number of barrels of X220 blended to produce economy. Once we have defined the variables, then we see that it's asking how many barrels of each type of crude oil to buy each week for blending to satisfy minimum cost. So our objective is to minimize the cost. We say minimize Z is equal to 30 X1 plus 30 X2, which are going to produce X100 is going to produce regular and economy, okay, plus 34.8 X3 plus 34.8 X4. Okay. Now it says that the regular produced weekly demand of regular grade of low NOx gasoline is at least 25,000 barrels, and regular is produced by these are the variables here. X1 number of barrels of X100 blended to produce regular, and X3 is the number of barrels of X220 blend to produce regular. And it's saying that the weekly demand for regular is at least 25,000 barrels. So we can say that X1 subject to X1 plus X3, X1 plus X3 greater or equal to 25,000. And then we have the same way it is asking for while demand for the economy is at least 32,000 barrels per week. So we can say that X2 and X4 are used to produce economy. X2 plus X4 should be greater or equal to 32,000. This is weekly demand. Then it says that at least 45% of each barrel of regular must be ingredient A. 45% of each barrel of regular must be ingredient A. So ingredient A is 0.35 in X hundreds, so which is X1, right? And plus 0.6 is also in X220, which is to produce regular. It says X3. It is asking that at least 45% of each barrel of regular must be ingredient A. So ingredient must be ingredient A at least 45%. So it should be greater or equal to 45%, which is X1 plus X3, blending by these two. Alright. And then another constraint is at most 50% of each barrel of economy should contain ingredient B. The ingredient B is 0.55, okay, which is asking about the atmospheric economy. So economy we see over here is X2 and X4. Alright. So 0.55 X2 plus 0.25 X4 should be at most, it says at most, so it is less or equal to 50% of each barrel of economy should contain ingredient B. So it is 0.5, and that is X2 plus X4 is the total of economy. So these are the four constraints. Of course, X1 and X2 and X3 and X4 should be greater or equal to 0. These two constraints are not written in a standard format. We can make it standard format. This constraint can be written as minus 0.1 X1 plus 0.15 X3 greater or equal to 0, and this constraint can be written here as 0.05 X2 minus 0.25 X4 should be less or equal to 0. So this is the formulation of this problem. Okay, let's see this problem. Product mix problem. Formulate a linear programming model for this problem to determine how many containers of each product to produce tomorrow in order to maximize the profits. The company makes 4 types of juice using orange, grapefruit, and pineapple. The following table shows the price and cost per quart of juice, 1 container of juice, as well as the number of kilograms of fruits required to produce 1 quart of juice. So we have the price of these products. We have orange juice per quart and price is there, grapefruit, pineapple, etc. And the cost per quart is 1.5, etc. Well, orange juice is 1, grapefruit juice is 0.5, etc. And we have 4 types of products they are making: orange juice, grapefruit juice, pineapple juice, and all in one. And how much the fruit required is given in the last column here. We have, for example, to make 1 quart of orange juice, we have 1 kilogram of oranges are needed. Similarly, for grapefruit, we have need 2 kilograms of grapefruit, and etc. For making all in one, which is dependent on orange, grapefruit, and pineapple, all in one type of juice, is 0.25 each kilogram of each is needed. Now the price is given, the cost is given, so we can find out the profits. The profit is 3 minus 1, for example, the orange for per quart. By the way, the quart is little less than 1 liter. So price per liter we can say, or price per quart over here given, no, it doesn't matter. Quart is little less than 1 liter. So orange juice is the profit is $2 here. We can say here the profit is 2. Here it is 1.5 and 1 and 2. Alright, this is the profit here, which is cost, price minus cost. Then the next slide shows on hand there are 400 kilogram of orange, 300 kilogram of grapefruit, and 200 kilogram of pineapples. So these are some right hand constraints are coming, which are telling us that how much kilograms of oranges and grapefruit and pineapples are available. The manager wants grapefruit juice to be used for no more than 30% of the total of the number of containers produced. He wants the ratio of the number of containers of orange juice to the number of containers of pineapple juice to be at least 7 to 5. Pineapple juice should not exceed 1/3 of the total product. So the idea is to formulate this linear programming model for this problem to determine how many containers of each product to produce tomorrow in order to maximize the profit. So we have to identify the decision variables and then define the decision variables, and of course then write down the objective function and of course constraint. So let's say x1 is equal to number of containers of orange juice, because it says how many containers of each product to produce. Containers of orange juice. And x2 is equal to number of containers of grapefruit. X3 is number of containers of pineapple. And then X4 of containers of all-in-one. And then the objective function is to maximize the profit. Maximize that is equal to, and we have the profit for each container. So 2x1 plus 1.5 x2 plus x3 or 1x3 if you like. No, sorry, this is 2.5 minus 1.5, so it is 1 here. 1 x3 and plus 2 x4 subject to. Now we have how many constraints we can see? We can see that first of all there are constraints about the weights. We have 400 kilogram of orange, 300 kilogram of grapefruit and 200 kilogram of pineapple. And we know that how much for making 1 quart of orange juice, how much kilogram is needed, grapefruit, etc., pineapple, and all-in-one is also using 0.25 kilogram each. So let's write down the constraints then. We have for orange, x1 is the number of containers of orange juice, plus we know that 0.25 kilogram of okay, 1 into x1, 1 kilogram of is needed for making 1 container of orange juice, and about 0.25 kilogram is needed to make of orange is needed to make all-in-one container. So it is x1 plus 0.25 kilogram is used in making the x4 container. So the total we have is 400 kilogram of orange constraint. All right, and then we have grapefruit, x1 plus rather 2, not x1. We have grapefruit is x2 and container of grapefruit juice, and the kilogram needed is 2 kilograms. So 2x2 plus 0.25 needed for making all-in-one grapefruit. So this is again less or equal to, total is available is 300 kilogram. So this is for grapefruit. And then we have 1.25 kilogram is needed for pineapple, plus pineapple is also used in all-in-one, so 0.25 x4, and the total pineapple available are 200 kilograms. So 200, this is pineapple. Then it says that the manager wants grapefruit juice to be used for no more than 30% of the number of containers produced. 30% of the number of containers produced. So we can see that the grapefruit is number of containers are x2. x2 should be less or equal to no more than 30%. So 0.3 of the total product. The total containers produced will be x1 plus x2 plus x3 plus x4. So this is maximum of grapefruit. And then it says that he wants the ratio of the number of containers of orange juice to the number of containers of pineapple juice to be at least 7 to 5. At least orange juice to the pineapple. So we have x1, it is saying pineapple juice, x1, x3, x1 over x3 should be greater or equal to 7 over 5. Orange to pineapple. Ratio orange to pineapple. And then we have should be greater or equal to 7, at least 7 to 5. Pineapple juice should not exceed 1/3 of the total product. Pineapple is x3, should be not less, should be less or equal to 1/3 of the total product. X1 plus x2 plus x3 plus x4. And of course x1 and x2 and x3 and x4 should be greater or equal to 0. So that's it. Let's go back to the slides here, and we have I can show you the slides. We have, this is the problem here, and these are the constraints here. And that's all for today. Thank you very much.